All right. All right. Here we are. This is Anchor, an explanation using Anchor. So this picture of a dog, when it says that it's a beagle, it highlights the regions of it that are beagle-like. And so the algorithm starts with the picture, and it says, okay, do I go to the pictures that are kind of similar to this, and what things do they have in common, and eventually selects the pixels around the beagle to say that they are...
Is it working? Oh, Scott.
We're on the internet!
Excuse Scott for when I turn off.
So yeah, that's Anchor to explain the dog. The opposite would be to say, what it is not, which, depending on your context, can actually make more sense. And so there are a bunch of techniques that work regardless of what model you've got. And those are really cool. Those techniques before are model specific. So like that picture thing, trying to explain the picture, you might want to explain the stuff that you're predicting from the class. And those kind of details are very tied to the model that you're using. A decision tree is like, it only works because it's a decision tree. But there's a bunch of techniques that work with any model, and you can use deep learning, or you can still use a decision tree and pass them into this thing and make pretty pictures and stuff. So these are a bunch of different plots and things that you can use with almost any model. And dependence plots, feature interaction and importance are all really common. The surrogate models are, Anchor is also by the author of Lime, and so you can get a more in-depth explanation of these from the book called, go back to it, the Christopher Molnar book, and there's this library called SHAP that has a good implementation of both, of most of these different techniques, and it's written in Python, and the stuff that it generates is like D3.js, so you can use it in your apps. And I'm going to do an example from the UCI German credit data set, and they have a great logo. So the data set is like 1,000 examples of a bunch of things that people could probably select to make a good prediction, but are probably also really biased. And different types of like bank information, and its purpose is to classify a person's credit risk. And so if you were to use this kind of data set to make a credit card prediction model and then go and use it, if you're in the US, then you'd have to explain all this stuff. And so you can grab that from UCI. They've got like an excellent repo of data sets that you can download. Also, AIF 360 from IBM has a copy of it, and so this code imports that, and then you split it into pieces. They have like classes that are all the different data sets you can get there, and so I just split it out, and then I use a pandas data frame, and I like convert the data set into one of those, and then Ravel flattens the target, which is credit, and then I split the data set into pieces. You do this because like you want to see that it works on data that it's never seen, and then you take a look at your data set. So the first step in doing a lot of algorithms is to just take a look at the data. Don't just kind of throw things at the wall and see what sticks. You can call .describe on a pandas data frame, and it will give you these nice charts in Jupyter, which actually this whole presentation is like code, and you can get it on GitHub, and I'll send a link in the Slack chat because I can't seem to get Binder to work. But like in Jupyter, you can make a presentation of it, for example, and so lots of good stuff with that. But taking a look at your data, Pair, which is a Google project, has an excellent data exploration tool called Dive and Overview. They're like 2 parts of facets, which is you like take a data set, you plug it into it, and it gives you a neat UI for exploring it. This is the other version of it, and for most data sets, you can also like get them on Kaggle and other different engines for reviewing them. So take a look at your data set before you start, and for the most part, if you're looking at your data, you're going to see what kind of things you could use in a model that would probably be predictive beforehand. You can also see like what kind of biases you would expect to have because the data going into it is biased. And then, so if you grab your stuff from Kaggle competition and you want to do the Kaggle thing, then you can grab XGBoost because that's pretty much all anybody ever does is grab XGBoost and then ensemble it the bits until you win by finding the flaws in the data set. It's usually how the game goes. So yeah, XGBoost classifier, and then fit, and then model.predict, and then you get like some predictions out of your model. And then you want to know like why it's doing what it's doing. This is a rock curve, kind of explains how well the model works. It's the area underneath is a common metric for that. Not great, but anyway, it's out of the box. That's what you get. And so now you've got that model, and then you want to explain it. And so the library that I mentioned before, Lundberg SHAP, you just import it and call it init.js, and it loads all the stuff for your Jupyter Notebook or for your browser or whatever system you're using to display this stuff. And then they've got different explainer models for deep learning and for decision trees and different types of algorithms. And then it breaks. Great. Luckily, I've got lots of plots. And so here's another one. This is a summary explanation of like why this particular algorithm did what it did. The first thing that it picked up was status A14, where A14 is whether or not they have a checking account. And when the feature value is red, it means that that value is high. If it's blue, then it's low. And this is binary, so it's either 1 or 0. And so it looks like if you have a checking account and that's present, then you're more likely to have a positive credit rating from this data set. And if you don't have a checking account, you're less likely to get one, and so on. And so it's also a ranked ordering of the things that are used in the model. And down at the very bottom, that seems to be a cutoff on the bottom there. The characteristic of whether or not they have a telephone number logged is not very important in the model for predicting credit. And so if you take this top feature here, status A14, and then you want to plot it in terms of like how it spreads out across the data set, the dependence plot, if you just call dependence plot on the name of it, it gives you one. And it's really straightforward. It picks the value which has the strongest interaction to kind of spread out the values, and then you can see that if you have no checking account, and then you're trying to buy a radio or a television, which is for some reason a category in this data set, then you're less likely to get credit if like you've got no checking account and then are trying to buy a TV. And then just to check like for seasonality in your data, the month actually seems to matter as to whether or not you can get credit. And it does have an impact, and it changes in time whether or not somebody's going to have a checking account. It looks like certain months they will open credit accounts. Here's a better one from a data set that looks a little bit better with this tool. But interaction plots show you how multiple features in your data set interact. And so all of this is coming from the SHAP tool. And so it looks like as you age, there's a split between male and female passing away. So the spread between the two variables of age seems to be present in this particular national health data set in terms of mortality. So this same library, which is explaining arbitrary data sets.
Could you go back to that last graph?
Yeah.
So is this saying that, males are blue. So males are more likely to die at age 60 than females?
Yes. And so up until a certain age, they're moving straight along, and people are aging and not dying. And then suddenly, the percentage of female deaths compared to the percentage of male deaths changes, and then the percentage of male deaths skyrockets.
Cool.
Oh, at the lower end, the separation at the low.
I have done it again. Sorry?
Over on
I got a minute here.
Just type in the headline now.
Separation,
Hmm?
You're
right?
saying
On the
there's
left
a
side, blue and red were separate.
Yeah. So it looks like up until a certain point that there's higher mortality, I guess, for females in this particular data set, whatever it means. So it also works for deep learning models. So those are like general things. You can just pass a data set into that and get those kind of plots. But deep learning, generally you have pictures, and so you use the deep lift thing, and it will tell you what parts of the picture are important for a deep learning model. So the MNIST dataset, it characterizes handwritten digits, and you can see that the red stuff is predictive of a class, and blue is not predictive of a class, and it tells you that like for multiple different instances, like what components of pictures tend to be important for making a particular prediction. The gradient explainer is a thing that can explain a single layer, whereas the other one explains the entire data set. And so like, if you want to identify a meerkat, it looks like you look at its face. And this weird looking bird thing, I guess it's a red-backed sandpiper, you look at its big nose. So it identifies what pieces of the picture are important. And there's a lot of great work from a project called Distill, which is like a open journal thing, and libraries like Keras, which they're used for explaining Keras-specific models, which is a popular deep learning library. So you can explain convolutional filters using activation maximization, and it draws these crazy looking filtery things that these are like the different textures and stuff that it's trying to pick up. There's also something called attention visualization. So attention models are super popular for figuring out like there are model specific reasons why they're popular, but like they also have this nice property where you can kind of figure out where models are looking, and you can see that the tiger's face is, I guess, a key component of identifying tigers. And you know, like I guess if you're looking at boats and you see waves and stuff, that seems to be pretty important. So these are like just libraries that you can download if you're trying to make a deep learning model that'll explain stuff. And you can use these things for debugging because these models are strange and they do weird stuff, and you try to figure out why. And these things will really help. So we'll talk about ethics in AI for a little bit. So fairness is huge. It's actually such a huge topic that I don't really want to dive in it too deep. There's dozens of conflicting definitions of fairness. So which is kind of funny. Like depending on the context, fairness means different things. So I just grabbed them from Google. Impartial and just treatment or behavior without favoritism or discrimination. So like if you are making an algorithm, everybody should be able to use it, and it should work. And like that almost never works. So like people are biased, and these models they kind of just find flaws in your data set and exploit them in order to do whatever it is you told them to do. Like they're really dumb, and if they recognize that like there's some stupid property of your pictures that like I don't know, there's like a black bar on the bottom of a particular category, it'll use that to identify that category instead of actually looking at the picture itself the way a human would. They cheat all the time. And like as humans, we create biased data sets, and they do bad things. Like if you have a data set that has only ever seen one kind of race, or like you're going to do a facial recognition task, then it won't work for categories of data that it's never seen. And there's a lot of cases where people have released sexist models in terms of word embeddings because of the annotations that were passed in. They happened to be that way, and then they didn't clean it up, and then they shipped it. And there's hundreds and hundreds of cases of people releasing AI libraries and tools and using them in the world, and then they're super biased one way or the other. And it's because people don't protect themselves from these issues happening, right? It doesn't happen by default. Your data always has these issues, and you need to prevent it, or your stuff is going to ship and it's going to look like this. So, like, you have to explain your models for these kind of reasons. In like credit, it's the law. But in terms of employment, admission, and lots of different use cases, people are more and more using AI, and these models are like as biased as things have always been, and they're picking up on data sets, and it's like an opportunity to address these issues. And not a lot of people are doing it. And so it's really important to review these things as you use AI. So there are a lot of tools for this. Here's a list. It's too small to even see. But almost every major player in AI has some kind of version of a set of like AI fairness tools, or an institute, or a project, or something related to AI. So like the bottom one is IBM's. There's New Institute from Facebook and Google. A lot of these stuff from these talks have come from different things that Google has released. And each of these libraries explain you can even see it. It's probably kind of small here. Like the different features that you measure in a data set to determine that you have biased data or a model that is skewed one way or the other, you will use these tools to figure out that you have these problems and then possibly weight your model or fix your data or whatever you can do to try to mitigate it. There's also like entire institutions and classes and books and conferences all related to this. And so how do you address this? Like your data is probably bad. It is bad. Like it doesn't really matter what you've done. When you make a selection of data, it is a selection. It's not going to be representative of everything. It can't be. And so it's probably going to have skewed samples, tainted samples, limited features, and a bunch of different kinds of things that you can measure to say that it's bad. But your data is bad. And so you can measure how bad it is and try to fix it. So imagine we are trying to make some sort of like skeet detector. And we have a data set, and it's just like the island of Newfoundland as input. And like that's a super biased sample. It's like one island. And like I get, you can be from anywhere and be skeet. And like so this data set's going to be the population of Newfoundland. It's going to be skewed a very particular way. And so if you look at it, there are a lot of minorities that probably wouldn't be well represented in this data set. So what are you going to do? You take the data set and you pare it down. 1% of the data set represents a class that it's not going to pick up very well. But then if you just balance the data set according to that, you might only have 2% of your original data set. And it's very difficult to get your model to actually use that. It won't be enough data for it to generalize. And so you can get around that. So you can make it small, and you can fix those issues with your data. But really what you need to do is collect a new data set, because that one's not going to work. And not a lot of people will do that. They'll take the data that they got, and then they'll just go and generate a biased model. And so then you go and you figure out a way around your model. Your data set is super biased, but like you figure it out. You use transfer learning, and then it turns out your model, the transfer learning data set was also biased in some weird way, and because it is still just more data, and it might not be data that you could even look at. So when you do this, your model is probably also bad, which kind of sucks. Like it's definitely going to be trained on bad data some way, somehow. And so the trick is, like you can fix it. So you've managed to get it to work because you use transfer learning, even though your data set was super small. But then you find out it's like, oh, okay, so we're trying to detect like, we pared it down, but like we're doing the skeet detector thing, and then we look at it and we're like, I don't know, it's something about like pineapple crush. It's like it's a local thing, but then there's like this weird skewed issue with the data set where it's like winter and there are like gloves for covering up the can, and we can never get a good shot of it. And so then you fix it and you like Photoshop in all these like cans of crush or something. I don't know what thing matters in this detection task. And then you go and you like make a model that works by augmenting your data set, and then you find like, nah, it actually doesn't matter. Like that's just like a drink that people like happen to have in the set that you're trying to predict or something, And so having done your due diligence, the trick is you just really need to document it. It's like any engineering task. You're never going to completely remove it, and you just have to try really, really hard to do so. It's so hard to do, and not a lot of people do it. And so the best you can do is to try it. And so having tried to remove it best you can, then you document that you've done that using something like model cards or data sheets for data models or data sets. These are some recent papers that describe ways that you can document data sets so that people can look at this stuff later. Those principles of good science apply to this stuff. And so if you can have good data provenance, which is like where the hell did this data come from, and reproducibility, then if you realize that your stuff is really bad, then you can go back and fix it possibly. If there's a particular set of things in your data set that shouldn't have been in there, then you can remove them. If you have the ability to iterate on it, then later on you can work on it. But also, if you can present these things to your peers, somebody else can scrutinize your models and fix them. If you keep track of these things, you might be able to fix your mistakes later. And model development is like an iterative process. So, like any good design, you want to get it in front of users quickly. And if you have the ability to iterate and go back and fix your models quickly, then you can just experiment. So you'll try something, and then somebody will like raise their hand and be like, "What the heck is that?" And then you'll go back and then you'll just fix it. And so if you involve your users, they're going to uncover these issues in ways that you can mitigate them, providing that you've got good reproducibility and you can actually iterate. So trust in AI is a really interesting topic because people trust AI way more than they ever should, and it's creepy and kind of worrying. So this picture is from a project that somebody did where they made this robot, and they brought people in and they said, we're testing the robot, and you're going to go through some series of tests involving the robot. And then as soon as the tests start, the fire alarm goes off in this building. And, oh, look, luckily we're here with the fire alarm robot. Wicked. And so the fire alarm robot goes down the hallway that doesn't go anywhere. And it's bright red, and it says emergency guide bot, and you're like, oh, Jesus. Okay, well, I mean, it might be experimental, but, like, I'm going to follow this robot because he seems to know where I'm going, where he's going there. And, like, they do this super realistic study. Like, there's actually, like, smoke billowing out of rooms. It smells like smoke. There's, like, fire alarms. People are freaking out. And the participants of this study followed the robot even when it just didn't go anywhere. Because people have, like, a weird trust in the AI for some reason that I don't know. I guess it's, like, an authority. Maybe people assume that it was trained on a lot of different data or something. And, like, people trust your models, and they shouldn't. So it's generally surprising how much people will trust models because the model says that you should trust it. And so you have to prepare for that because, like, if you're giving them bad data, then it's on you to, if you know they're going to trust it, to make that data good. But on the other side of it, there will be things where you need them to trust it, and they won't, which is probably the better of the two options. And so the trick is to make your stuff very trustworthy. So the trick is not really to get people to trust you, because apparently you can fool them into trusting you anyway for some reason. So the trick is to make things trustworthy. So the principles that I mentioned before, if models are explainable in, like, human terms, they can look at it and they can understand what's going on. If they can look at the data set, see where it came from. If people can scrutinize the model and scrutinize the things that are coming out of it, then those models are inherently more trustworthy. Like, they're worthy of trust rather than expecting people to trust them. People should have the right degree of trust in the thing. So, as you go home and you find that your, you got like a Google Home or something in your house, and then you look at it and you find, well, I actually don't know how this thing works, and, like, if your data is being collected somewhere and you're using the models that are being generated from it, like, you kind of need to investigate. Like, am I trusting this for the right reasons? But if you're the one making these things, then you also got to investigate, like, ways that you can get people to trust your stuff. So if you want to increase trust in your models, fairness, robustness, explainability, and lineage are all key components to making models that people can trust. Privacy is a key thing because these things all run off data. People are trying to collect massive amounts of it even though they don't know exactly what they're doing. They'll just collect it anyway. And then you end up with huge privacy breaches because they collected it and then they lost it. And there's a lot of PII out there now. So in addition to, like, security risks, people, when you have somebody's data and you're treating it as data, that's one thing, but, like, there's new weird things that you're doing with models that you kind of got to pay attention to. In Canada, there's PIPEDA, and Europe's GDPR, again, they protect user data. So, like, if you are not careful with data and you're just goofing around, there are big financial reasons for not messing up. It's important. There are laws around it. And you're building models from this data, but these models could actually then be made of that data. And so you got to be careful. So deep learning models can be fooled by something that Ian Goodfellow called an adversarial attack, where, I don't know if you've ever seen this, but you can make a particular picture of, say, a school bus that has been injected with pixels in just the right spot, and for a whole variety of different machine learning algorithms, and like, it could be the API from Google, or it could be one from Amazon, or whatever, all of them will look at that picture of a school bus or a human would look at as being a picture of a school bus, and then call it a monkey, or like whatever thing it needs to be. And you can actually create these adversarial images and put them on T-shirts and wear them around. And if you're in the vicinity of some kind of camera that's looking at it, it will actually recognize that wrong. And so if you're trying to, there's trust that goes two ways. There's trusting your user and trusting your stuff, and then there's also trusting in the system to not be attacked. So like your system will be attacked probably, and there's lots of different ways that can happen for even simple models. Like so that's a deep learning image recognition issue, but in just a regular data set, if you've got private information and there are sensitive values in there, and you know some stuff about that, if you can find similar values in there, then you could probably extract data from that model. So if people are allowed to hammer your API, then it's possible that they can extract the data that was in that original API. So like here's an example of a person's face. This is like the original one, and they were able to recover a face that was in the model from the from the original training data. They could pull out a face, right? And so just to go back to these, so there's certain aspects of similarity that you can abuse in order to get data out. And the top one about adversarial attacks is generally abusing the nature of deep learning models and how they make their predictions to get it to make the wrong prediction.
So, sorry, Jordan.
Yep.
For that particular attack there, the attackers had access to the model itself, or they had access to the training data?
They don't have access to the training data, that's private, but you've exposed the model. So if you're Amazon and you release some kind of image recognition API, like every major cloud provider has, and that data was probably made from, I don't know, the entirety of the internet, or maybe all of Facebook's users or something, then if you're able to, as a developer, hammer that API, then you can actually extract that data in some cases, depending on the case. Like, here's a really simple example. Like, if you've got a data set that includes, for some reason, wealth, and you look at all St. John's, there's a couple of individuals who would have, like, perhaps abnormally high wealth, or they're known in the community, or they have particular attributes. Maybe like you have like a sunshine list or something, and you know that data is probably in the data set. Then you can leverage that. So if this data set is somehow linked to health records, you might be able to find that there's a particularly wealthy outlier, or there's a region of the model that behaves when it sees it behaves a certain way when it sees wealth, and it seems to be predicting a certain disease. You could probably infer then that there was a wealthy individual in the data set or in the community that has that disease, and then end up leaking information about an important person or something. And like, I don't know, that's kind of driving. But like, there are better examples of that. Your data can be leaked through your model, and it is PII like anything else. So you have to restrict access to it. But a lot of people, when they produce an API, it's public to the internet, and it's not always locked down like that because the PII is hidden away, and the model is just making a prediction, right? So yeah, so these are all issues, but the trick is to involve your users and design with AI in mind. A lot of principles of regular design, like I don't know if anybody's heard of a Norman door where the handle's messed up and you push and you pull and all those things. Design of everyday thing has a bunch of suggestions for designing things in general, and AI is a thing, and so these principles still apply. Visibility about the things that you can see when you're making some kind of thing that involves AI. Affordance, like cues for interaction. Mapping between controls and effect. If you see an icon that's familiar, you expect it to do a certain thing. Then you click on it, and if the thing changes a little bit, then you're like, oh yeah, it actually did process my input. Constraints about like what you can do and not do. So like you could cue somebody to say that an icon's not clickable, and by making it gray, and then constraining things that are available will guide the things that people try to do, and consistency, learning from patterns. So you gray out something instead of hiding it, and those kind of things. These components all still apply to ML. So if things are making a prediction, then you expect it to kind of make similar predictions in similar contexts. So it's like consistency. In terms of feedback and interaction, you can provide from the explainable AI part different kinds of feedbacks and responses, mappings according to like given inputs. You can like all the principles still apply to AI, and so depending on your context, you keep these things in mind as you make your system. Then you should design something that is usable. AI is like it's not special. It's not magic. So the way to make things that involve AI that work in ways that you expect them to is to focus on people first. So yeah, this is completely stolen from just overall like all the words and everything like that. So don't expect machine learning to figure out what problems to solve. This is something that you have to do. If you're not aligned with the human need, then you're going to make something that is useless. Like a lot of things that I keep hearing about are like, built with AI, and they'll throw that in as like a marketing thing or something. And if you don't need it, don't do it, right? Like as I said earlier, the most explainable model is like a heuristic. If you look at a picture and you've got this thing and it says like, things in the picture, like just do simple stuff. Because if you don't, then you make complicated things that are useless. Like Ketchup Bot, but he's great. So make Ketchup Bot. But like, ask if ML like even has any business in being in your app. Because like here's an example. Gmail, right? It's looking for attachments and like, oh, Google, they're definitely using AI. And like, if you're trying to write a message and you read the word attached in it, it's going to be like, oh, hey, attached. You probably forgot something. There's no files attached, and you should attach something. Like you can create these kind of interactions. So, like, if you're working on that, you can just use a regular pattern match. You can find the word attached, and if it contains attached, then you should probably prompt them with this thing here. But a lot of people would probably be like, I'm working on this thing, and I got an API for like string recognition. I should probably use it. Like, don't, Like, keep it simple, and don't use AI unless it really fits your use case. So to determine that, you look at the way that a human expert would perform the current task. So, like, if your human's going to do it, then, like, you can mock out the thing through looking at human interaction. If a person was doing it, doing whatever your task is, like looking at that email, they're going to scan it over and say, hey, attached. Oh, you didn't attach it, right? So if that's what the human does, then you got to make your bot do that. And if that's all it's doing, then you don't really need to make a bot, and you just write regular code that finds the thing. And so then if it doesn't work, you also have to consider the 4 parts of the confusion matrix. And so I'll get that in a second. But like if a human was doing this, you also have to consider like their assumptions and their responses. So yeah, step 1, actually use a human. Because of that last point, if you're going to make something with AI, don't actually start writing code, like whiteboard it, and then like wireframe it, and then just mess around. Like if you're going to release an API that makes suggestions, V1 of the API could actually be people making suggestions. You could use Mechanical Turk or something. Like plug people into your system until you figure out the usability in a way that makes sense for you to invest in putting the AI in there. Now, like the AI might be an easier thing to get these days, but it doesn't mean you should really be using it. So Wizard of Oz experiments are where there's a man behind the curtain, and you just replace the AI with humans until you figure out what the thing's supposed to do, and then you write the wizard. Here's an example that Google used. So they click on this thing, and when you do a search, the first thing that comes back is human generated. And eventually, when people are using it, they figure out what kind of things this AI needs to be producing. And through that, you can make something that works, and you can get it out faster, but then also you're making something that actually works correctly. You've got to consider false positives and false negatives, which is you do something and you were not supposed to have done it for the 2 cases of the thing guessed it right and the thing guessing it wrong. The confusion matrix, there's 4 components. There is false positives, which is like you said that something was bad and it wasn't, and false negatives where you it's the other way around. Now I'm getting confused. Yeah, this is a confusion matrix. Yeah, like a false positive is when you predict somebody, say, would not have a disease when they actually do. And a false positive is where you would say predict that somebody who does not have a disease and like you treat them and you're not supposed to. So like the impacts of that are pretty big. And so if you're making an AI system, you have to consider like the four components of this curve here, which are like you got it right for the right reason, you got it wrong, so you got it right and you got it wrong, but then it was right and it was wrong. Like all those four components need to be considered, and like how your user is going to interact with them. So you can make trade-offs. Like if you can't tolerate a missed crime, then you're probably going to cry wolf once in a while. So if you make some kind of system that detects crime, then you're probably going to want to fire some warnings that were not actually appropriate. But then that's bad. Like your user's going to look at that and be like, oh no, I'm getting all this crap I got to review. And so then you got to look at usability testing. There's ways that you can mitigate that impact by making it not so bad that things have been flagged wrong. And so part of that is human in the loop AI and adaptation. So people, when they're trying to understand your model, they're probably going to do it wrong. Like this is obviously not a face, but it's obviously a face. So they're going to look at your model and think that it's doing a certain thing for a certain reason, but like it's not a set of rules, and it might not actually be doing things for any reason. So you collect their feedback and you try to figure out what they actually do think about it. Google does this in terms of like, is this useful right now? Is this spam? You can flag things in different ways, and you collect that feedback and then you improve your model. If somebody leaves a comment, then like it's super valuable. And if you can collect enough of this data, you can actually pump it right back into the model and fix it. And you're going to learn as your model learns. So XKCD, you just keep stirring the pile. You're going to make a model and it's going to be wrong, and it's not going to work, or it's going to solve the wrong problem. And as you go, you're going to figure out what things you should have done up front. An important part of the whole process is labeling data. So if you've got the wrong labels, you're going to teach the AI to do something that it's not supposed to be doing. So the issue with that is like your labels can't be collected until you know exactly what you need, and then you don't know what you need until you've trained the model. So it's sort of like this weird chicken and the egg issue, where if you're going to make a big system for collecting this feedback, yes or no, and then you look at like your model and you want to train it and you don't have that data yet, then how is it that you're supposed to train the model until it's been released, and then you got to release it broken and then collect that feedback or something? And it gets kind of tricky, which is why you basically have to fake it until it works. And then through interacting with your users, you can figure out what things you should have been collecting for data, train a better model, release it, and then fine-tune it. And a key part of labeling is also allowing for truthiness. So when you label something, it might be really tempting to just like call it one bucket or another, or have like a binary, like it is the thing or it is not. If you do that, then you don't really reflect the real world in a lot of different cases, because to say that something is a category of cat, you end up getting into this weird, like, what exactly is a cat? And so it's hard to annotate things with these binary labels. So you might want to add things like tags and have piles of different labels that I think could have. Or to say that something is true or false, you might instead say that it is close to being right or it is close to being wrong. And that's it. Those are different ways that you can improve AI. Yeah. Any questions?
So, yeah, in that example you had where you had 59 columns and 1,000 samples for credits, so what was the dependent variable there? What were they actually trying to figure out?
We'll go back to that. So you've got all of these different features which represent different inputs to the model, and the thing that you're trying to predict is whether or not it's I believe a Boolean label of whether or not you should provide them the loan.
Right. And where does that come from? Where does that Boolean come from?
So that's the whole thing. It came from whether or not they gave them a loan.
Right. So this is just a method to automate the mistakes that people have been making without the expense of paying people to make those mistakes.
Exactly.
All right.
Yeah, you just duplicate whatever the data was in the first place. But the thing is, when you did it the first time, you didn't have a bunch of data there in the same place. And it maybe wasn't easy to do the statistics because it was 100 different people doing it and you didn't quite notice who was giving who loans. And then at the end of it, you look at it and you're like, oh, that guy over there is always giving people money and he shouldn't have been doing it. Or vice versa. And then you can go and look at your data and fix it. And so this is an opportunity to fix those data sets before you go and automate into things like a whole bunch of biases that you never should have done in the first place.
Yeah. So you get a more consistent, answers.
And that's the other thing. AI,
more predictability.
yeah, it can be. Like at least you can make it do the same thing. It's a good property for it to have. It might not be though. You know, it depends on the data and the model and all these different
But
attributes.
in that example, what you really want to do is look at whether the person defaulted on the loan in the end, right? So,
Yeah,
so
and
you collect the data, you give everybody a loan, see who defaults.
yeah,
Now you got valuable data.
very
right?
very costly though.
Yeah, expensive to collect good data.
But that's the thing. The value of the data is sort of it's not free, right? The more valuable it is, it tends to be more costly. So Stripe is a payment processing engine that you can use to incorporate like credit cards into your website. They actually allow a certain random small proportion to go through so that they can learn exactly what real fraud looks like. They have to do that. And if they didn't do that, they would have no examples of fraud. And you end up with a lot of weird issues with drift and things. And but it comes at such a huge cost. But they're very controlled in how they allow these things to happen in order to collect these better labels. But those are the kind of extreme things that they might have to do if they weren't careful in collecting the data in the first place. So you got to be careful with the data set you were just handed. Another example that I've heard is somebody was trying to predict something about recidivism. And so they were looking at a bunch of prisoners who were up for parole, and the thing that they were predicting is whether or not somebody would allow them parole. They weren't really predicting whether or not they were going to end up committing additional crimes because of the way the data was structured. And then this thing ended up rolling out, and it was super biased in all kinds of ways that ended up just mimicking the ways that humans did things previously, and it was a huge mess.
And that's, but it's still being used.
And that's the thing, yeah.
Those models are being used in practice in the United States anyway. I don't know if they're being used in Canada.
Yeah.
They are used to help make parole decisions.
Yeah, absolutely.
And sentencing decisions.
And they're used. Everybody is affected by these things. Right now, like everybody in this room has probably been processed through some model like this that has been biased because a lot of people driving, they got insurance, and the cost of insurance is coming out of a month. The thing is, a lot of these are also like proprietary and secret, and if you're not open about where it came from, you don't even necessarily need to open it up because there are security risks. But if you make it in such a way where it could be scrutinized, and then you allow it scrutiny, say like, I don't know, get somebody to sign an NDA and go and look at it, or whatever kind of things need to be done, then at least you can do that. But a lot of these are like super locked down, and I think if something is affecting the public in this way, it needs to be transparent. It's not just about like, hey, we denied you, and here's ABC why we did. Like, you've got to kind of explain the entire process, like why A, B, and C,
Or you might not even know the model's being used.
And that's the other thing. Like, if AI is being used,
Yeah.
But I don't know. People do get weird about that. This is the whole thing about trust. That there are cases where you're like, oh my god, that model is so bad, but it's probably bad because it was trained on bad data, but it still might outperform people. And if that's the case, while you might be super worried about the AI because it's weird, then like it's also there might be some kind of benefit about it that you should probably take advantage of. People get worried that, oh no, it's wrong. Yeah, but like people are more wrong. Like if you're worried about a self-driving car because like what if it crashes into people and causes an accident? And it's like, man, everybody does that all the time, you know? It might actually be safer even though it's still not perfect.
So what's your take on self-driving cars? It got really intense there.
They're not going to work around here.
Why not?
Just the potholes you go by.
Yeah, see, like the thing is, these models only work on the data that they've been trained on, and a good training ground for a self-driving car is not a place where you would be able to keep testing that car. You know, like around here, that self-driving robot is totally going to end up on the side of the road. It's going to hit a moose. It's going to do some crazy thing that, like, probably wouldn't have happened in California or whatever where it was trained. And so, while I'd like to have one, I guess, if it was super safe, I don't feel like it's going to work around here. But you know, I think they're coming, and they're going to replace a lot of transportation things that we currently use. Because, like, while they're probably not safe for all these different reasons, that's only around here. You know, there's lots of places where it still will work, and so they're going to exist. They're going to get better, and then eventually, when they work good enough, the edge case of running in Newfoundland, that'll happen. So.
Don't they need just to be better than the average human?
Yeah, but people want it to be much better, right?
Yes.
Sometimes that's a
but
little hard.
It would be sufficient if they would be better than the average human, huh?
It's kind of it's a weird place to be making. To be discussing things, because then you end up having to measure humans, and then you realize that a lot of the things people are doing they shouldn't be, and that's where a lot of this.
That's why I'm pushing you there, because I mean,
yeah,
we're expecting much more reliability from AI than actually we're expecting from human.
Yeah.
So that's just something we're measuring with two different.
Yeah, it's two different thresholds.
Yes.
But
and I can understand it's kind of human psychology, but it doesn't really make sense.
Yeah, and there's a lot of things in ethics. It's a huge point of discussion, and it gets really messy really quickly. Like the whole thing about fairness and like what is fair, because you know depending what you're doing, like allocating things and whatever, like fairness isn't always fair. It's got a lot of weird paradoxes and stuff. So. I think before we really figure it out, there's a lot of things about transparency we need to figure out first. Back?
So, what are some of the ways to like reduce or bias in your data?
So there were more examples in this, and I didn't know how long it would be, and it was actually shorter than I thought it would be. So here's another internet. I'm just going to show you the example that is actually on the credit data set, but I didn't include. All right, so that same credit data set that I showed before, I chose because it was using this example. And I was going to use it right on through, and then I didn't actually write off code. So these guys pull the German credit data set, and then they compute fairness on a particular metric, and they pick something and they say, hey, for this thing here, what are the two groups, privileged and underprivileged? And then how disparate is this thing in the data set? So the thing that they look at is, I'm thinking gender. I think I found this example confusing. Yeah, okay, personal status and sex was removed, and the thing that they're looking at, the protected class, is age. So the question was whether or not they allow young people to have loans, because for whatever reason, they like in terms of personal status, marital status, sex and age, like there were lots of different biases in how loans had been allocated previously. So when you use this data set to go make a model, And then they are looking at the difference in outcomes just based on the current prediction that people have already made, and between the privileged and underprivileged group of over and above 30, and then they measure this score. There are a bunch of different labels and metrics that you can use to do these things, but they measure that score, and then they figure out exactly how much that data set has been skewed so that your age matters in terms of the loan, and then they scale the data set so that the outcomes are not showing that anymore, and then after they scale it, then they see that the unprivileged and privileged groups have no difference in terms of that one variable. The caveat here is that in order to do that, they ended up skewing it in all kinds of other ways. And you can't actually know all the different strata of your group. There's certain things that just haven't been recorded that when you do these things, you end up creating additional biases. It's really kind of messy, but in this particular case, the thing that they really cared about, they removed from the data set first. And then when that data set was balanced in terms of age, then you go train a model. And the model will do generally whatever the data set had been doing before. So then you just use the data set as it was. The other technique you can do is, if you didn't remove it from the data set, then you can make your model predict stuff differently. So if you have something like a neural net, you can modify your loss function so that it has a penalty for fairness. There's a recent article about women snowboard too. And so the captions that they had gathered from I don't know where, somewhere on the internet, included a lot of male snowboarders. And so whenever they saw somebody snowboarding and they wanted to annotate the image that said, there's somebody snowboarding, and there's a tree or whatever description they give for the auto captioner, it would generally use like male pronouns. And so what they did is they made a model that would modify itself so that when it made a prediction, it was less likely to use male pronouns and just use general ones. And it gave it more points if it wasn't biased in terms of gender. And then the last thing that you could do is if you can't really mess with your model for whatever reason, you're required to use a particular kind of model, then when your output comes out of the model, then you could scan over it. And so in this case, you would go and just Control F for man and replace it with person, and adjust it in post.
What's the usability and user experience for systems that are powered by AI? From the user's perspective, they don't know where the results are coming from. So how are we, or is there a way to effectively evaluate how a user perceives or how a user trusts that system, whether it's AI generated or human generated?
Ask them if it's using AI. You know that whole any sufficiently advanced technology is indistinguishable from magic? AI is everything that we don't fully understand. So if you're super transparent about how everything works, then you just ask people about your system. Like they're just talking to them. Just call them up and see what they think about it. There are measures that you can use for trust. So it kind of, the details, the context matters a lot. But if you trust the result, you could do something like present a confidence score in terms of your prediction that you've made, and then ask them if they agree with it. Like when you rate the quality of a call or whatever, just additional comments about the quality of predictions. It ties right into your regular usability to say did this thing work? And to figure out whether or not they trust it, then if they stop scoring it poorly, then you can perhaps assume that they've started to trust it, and you have to make some different stretches, but there's no substitute for actually just asking. Is that it? Thanks. Cool. Thank you very much, guys.
Awesome. Thanks so much, Jordan. Yeah. Congrats to, I don't think he's here, I don't see Mike here, but congrats to Mike on an awesome game jam that happened, I think last weekend. There's 6 games coming out of that, but all the games are on Game Dev NL if you're interested in game development and stuff like that, so too bad you can't go to the game jam because it's in the past now, but at least you can go check out the games that came out of it and see what happened there and maybe attend the next one. Also, don't forget about the food bank. So yeah, if you want to help out there, go to their website. Is there anything else happening in the community for software developers that anybody wants to pitch? Anybody have any announcements? Anybody hiring? Stuff like that? Yes.
We hiring.
You're hiring. But I don't know how long this is. You probably just yell.
Yeah, we are a small startup company. We have a special kind of drone system. I know everyone thinks he knows what we're doing. No, we have actually a drone system which has a docking station, so it's completely hands-off. So it's for military applications, for security applications, and the aim will be completely autonomous. So there's a lot of vision processing involved and machine learning, as they mentioned, not AI, and other things in that field. So we are a really small startup right now, and we just got a really good contract, and so we're looking actually for people who are interested to build really cool robots.
Cool. Thanks.
What's the name of the company?
AS Works. Just approach me, I will be a few minutes around.
Awesome. Anything else going on?
I believe Colab Software's hiring. I've heard of those people before.
They sound like a group of cool, attractive people. Yes. All right. So look up Colab Software. They're hiring people.
Yeah.
And
Anna Learning Code is looking for mentors if anyone is interested.
I've heard they're cool too.
Yeah, they're cool. Sometimes we do workshops a couple times a month, and basically what we do is we target towards people who don't know any coding at all, but are in marginalized groups such as women, trans, non-binary, whatever. Some are youth programming, and some is adult programming. So we have like whatever you're more comfortable with, and basically you just show up the day of and help out whoever you can. So it's really low commitment. And if you're interested in more of it, you just go to canadalearningcode.ca and sign up.
sweet. So yeah, if there's nothing else. If you're not already part of the Slack group, go to slack.ndev.co and you'll be able to sign up there. It's a pretty active community. There's a whole bunch of people on there. Good resources. People have been asking, help for various programming problems or whatever, and people generally pitch in or talk about new libraries that are coming out and stuff. So it's a really good group there. And other than that, if you have or know of anybody who has an idea for a talk or would like to give a talk in the future, get in touch with either myself or Scott via the Slack, or you can probably get us from the meetup group as well, and we'll slot you in the future sometime. And I think that's it for announcements. Thanks everybody for coming out, and we'll see you next time. Happy January.